Great, thank you, and good afternoon, everyone. So I'm excited to talk about our work on enabling end-user programming via leveraging program synthesis and constructing derivations that have holes in them to account for incomplete information. This is joint work with João Costa Seco, who is actually the real inspirational lead behind this project. I'm very sorry he couldn't make it here, but he's online despite the early morning hours in Portugal, and I hope he can maybe join for the Q&A session. And also Luis Carvalho, who implemented the demo that I'll show you later on, and my colleagues Bernardo Tonino and Carla Ferreira, all at the Nova School for Science and Technology. So in the recent couple of decades, there's been a lot of work on leveraging programming language artifacts that have holes and trying to deal with those explicitly in some way. One of the earliest approach was holes in sketches. Sketches are the outlines of programs, and we leave holes in them that we don't want to synthesize. So this was some seminal work by Armando Solar Lezama. And since then, we've looked at other kinds of artifacts with holes. So Cyrus did some work with Hazelnut in providing editor support for programs that were incomplete and had holes that hadn't been written by programmers so far. Certainly, people who work with theorem provers have dealt with holes in proofs for a while. So a hole in a proof might represent a goal to be accomplished to help take the next step towards completing a proof in a language like Agda. And IDEs can help kind of manage where the holes are and filling them in. And we're looking at perhaps a specialization of holes in proofs, holes in particular in derivations that are formed from inference rules. These holes represent facts that we don't know, but that we need to know to complete a derivation. And we're going to use this in the context of logic-based synthesis to deal with this missing information. So the context of our work is on a project where we're trying to do synthesis for low-code programming. In particular, we're working with an industrial partner, OutSystems, that has a low-code platform. And we're building a system called Golem, which is supposed to kind of carry this to the next level. The concept here is that an end user might describe a program that they want to write using a natural language description. And then we use various kinds of natural language processing technology to turn that natural language description into a set of facts. And these facts basically reference concepts in an ontology. And then we have built a template-based program synthesis approach that uses logical rules to turn those concepts in the ontology into a derivation whose conclusion specifies the application code that we want to synthesize. So this is the vision, but there's a challenge here, right? Which is that in reality, end user programmers leave things out. So, the description of the program that the user wants to synthesize is incomplete in many cases. The end user programmer may not know what they need to specify. And so when we apply natural language processing, what we get is essentially a partial set of concepts, right? We get some facts that are useful for synthesis, but we don't necessarily get everything we need. And so our strategy here is to produce a derivation, but it may have holes in it representing that missing information. And so the conclusion of that derivation is really the outline of an application, but we still need to fill some things in. So what we do is we pass this derivation to a suggestion engine, which then makes perhaps suggestions to the end user about how to fill these things in. Maybe the question is, what data type do you want to apply this to? And then there might be several choices, right? Or where do you want to show this information? There might be several pages. Or perhaps, actually, we don't have anything to suggest, but we can just ask the user a question and they can give us that information. And so this goes into the loop where we get additional concepts and eventually can fill in the holes in the derivation. So let's illustrate the approach with a concrete example. Let's imagine our end user programmer says, I want to show a list of products. In this example, the user is using natural language. That'll be the focus of this talk. But in the larger Golem project, we're interested in capturing intent in other kinds of ways. It could be gestures, could be choices from a menu, could be input output examples. But for now, let's focus on this idea of natural language. I want to show a list of products. How do we turn that into a set of concepts in the ontology? So this is actually not the focus of this paper, but we're leveraging some research by collaborators in the project that can turn this into a set of facts. And so these facts are basically predicates in a logic, and they represent the original utterance in terms that the logic can understand. So for this example, I want to show a list of projects. We have a concept called show, which means that we're going to display something on the screen. We need to know what to show. In this case, we want to show products, and there's indication that product is some kind of data structure or record here. Now, we might also have some background facts, right? So in general, this is a tool not just for creation of programs, but for evolution of programs. And so we might have information around that says, oh, there's already a concept called product in this application. Products have, names, price, a list of stock, maybe some other information. So we can combine what the user tells us with some background information as the basis for program synthesis. So let's look at the next step, going from those concepts in the ontology to a derivation specifying application code. This is more the focus of the talk today. So we're going to use rule-based synthesis. We have a collection of facts. We have a collection of rules. We want to put those facts together and see what we can derive from them. So in this case, we have 4 facts that we want to show something, that we want to show the product, that the product is a record, and that is associated with a database entity that has these fields. So one example rule we could apply, there's a set of rules in the paper, but one of them looks like this. If we know we want to show an entity and the entity is a record, then we can connect these two with a what record judgment that just serves to connect those. Presumably product could be something other than a record, and so there would be other choices in that case. But the next step perhaps is more interesting. If we want to show something, we know it's a record, we know it's connected to an entity, then this is something we can actually make a query in the database, right? So we form a query out of these things, and we're basically building up this tree. Now the next step, actually in this example, we're almost done. We have a rule whose conclusion is actually a predicate that mirrors the signature of a template in our component-based synthesis library, right? So we have a library that knows about lists and can instantiate them with this template, and we just need to plug in, these items. And these items come from the premises. They're free variables. And so we match those premises to the things we have, and we find out, okay, we have something to show. We have a query. The query, tells us how to get the basic data, but there's some missing pieces. Right. In fact, the missing pieces are, we're trying to show something. Where should we show it? There's some kind of a notion of a page in the application, or maybe a pane that's part of a larger page. And what attributes of the product should be shown, right? So this product has, a name and a price and a stock, but we might not want to show all of those things. And so we need the user to provide us with some additional information about, which attributes need to show. And in fact, of course, if the entity actually had 10 or 20 attributes, you can imagine it would be very awkward to show them all. So we do need this information. We don't have it. So the challenge is basically we can't synthesize a program based on these inference rules in the case that information is missing. And, one could blame the user, but I think it's an inherent problem in this domain, right? We have non-expert users. These end users will provide us with incomplete information. The question is, how can we deal with it in a kind of a nice way, right? So the idea we are proposing here is to allow some of these rule premises to be deferred. And these deferred premises, when they're not provided, they'll create holes in our synthesized derivations, and then we'll fill in the missing information later. So again, to go back to a concrete illustration, here I've rewritten the rule, but I've marked 3 of the premises as deferred. So a deferred premise is one that might be missing, and it's okay if it's missing. In that case, we'll just kind of go on and then come back to it later. Now, you might ask, why are some premises deferred and not others? So I'll give a quick answer now and come back to this later. But basically, we want to pick premises that are essential in the sense of controlling the structure of the derivation. That we want to show something is enough to tell us that we're going to use the list template in this simple example. And so we'll make that one required, but the others are all kind of, additional information that's needed to refine the basic thing that we're trying to show. So we'll come back to this question later, but that's the intuition here you should be thinking of. So in this case, we do have the required piece, the show piece. We have the query, which is another potentially deferred premise, but we have it, so we won't defer it. And we can build, the next piece of the derivation here. But now we have two holes because there are two premises that we actually didn't have data for. Information about the location and information about the attributes. So how do we fill these? Essentially, we need to do this in order to actually instantiate this final template and build the final application. So what we're going to do is we have this derivation. Some branches are complete, some are not complete. What we're going to do is we're going to do backwards reasoning. And the idea is to go from kind of a high level or an application level view of what we're missing to the level of abstraction at which the programmer or the end user is going to interact with the system and find those primitive pieces that we can actually ask the user about. Because the concepts we're missing might be more complicated and harder to ask the user, at least a non-expert user, directly. So we're going to go back and see what's missing, right? In this case, one thing is where to show the data. So that's clear. We have to provide that. There's also this page predicate, which basically says, this page is a page and not something else. We might have some candidate pages in the app, so that's where we can get these suggestions for possible instantiations of these predicates. Over here, we might be able to derive the attribute from a query, which we already have, from some information that relates fields to the query and a choice of which fields, right? So this is the question about what to show. So broadly, we have our derivation result, which is this thing we want to build, but we're missing a few variables from it. There's these free variables P and A, and we have these open questions or holes that we want to fill in, which are also predicates at a slightly higher level, at a level where we can actually ask the user for insight about these. So now there's several ways we could potentially gather this missing data. Considering the attribute hole, what could we do? Well, the products query is related to a data structure. That data structure has certain fields. So one thing we can do is just show the user a list of them and ask them to pick which ones you want to show, right? If we don't have the information about what's in those fields, maybe this is the first time the user has mentioned products, then we can just ask the user, what's the data in products that I can get out. More generally, there might be, if there's many choices, perhaps we could use some kind of learning mechanism to prioritize them. Right now, basically, user interaction is the only thing we've implemented, but I just want to point out that there's a space of possibilities here from, writing more inference rules for suggestions to AI to the simple approach that we've implemented so far. So we do have an implementation. It's a prototype in Haskell. A derivation is represented with a sequent, as in the idea of a sequent calculus. So a sequent calculus carries both kind of the assumptions that you're building on and the thing that you're currently trying to derive. And so that's exactly what we're doing. The context is basically the deferred facts, the things we're missing so far, and the conclusion is the thing that we've been able to build up. And then free variables kind of connect those, right? So the conclusion has some free variables like the set of attributes we need to define, and one of the deferred facts is the thing that's going to generate that free variable. So using this data structure, we build on a Haskell library called the logic library, which implements backtracking logic programming in a monad. And we're going to use backtracking search to generate all possible derivations, given the available facts we have. And so then we'll interact with the user basically to select, if there's more than one derivation that's possible, we might have different structures. We'll select one of those derivations. The template at the end, do you want to show a list? Do you want to show a search box? That might help the user choose among them. But then once you've chosen a derivation, then you ask about the information or the holes in that particular derivation that might be missing. So to give you a more concrete idea of how this works, Okay, so right, let me come back to that design decision. So you notice there's search here, right? We're searching for a space of derivations that we can produce given facts, and given the fact that some things might be missing, we could produce multiple results from this, perhaps, right? And so actually the reason we don't want to make all premises deferred is that the proof search would be too unconstrained. Right, so actually the choice of which premises to defer basically drives how many derivations are possible, and it's a kind of way of expressing the intent of the designer of this logical system regarding how we should search for proofs. So I think, I can't tell you exactly how to do it, but I think the principle is this idea that we want to defer premises that are conceptually independent of the main line of the derivation, and aren't central to its structure. So we can ask them independently without blowing up the set of derivations that we construct during search. I think an important piece of future work is, kind of looking at disciplines for this choice in more depth. How do you actually design these things? Maybe there's formal properties to check. So I think it's an area we'd like to explore some more. But like I said, we do have a preliminary implementation, and I'm going to turn it over to a video that Luis Carvalho recorded to show you how it works in an example similar to the one I've been outlining.
This is the starting point of the application. So we have an already existing page called homepage, still empty, and we have a database table called product with attributes name, price, and stock. So we can start writing our first instruction here. Let's say I want the page to create products. And this sentence is represented by the following ontology facts. So in this case, we are missing a detail saying which is the page on which we want to create the products. So the first question our tool proposes is using the already existing page called homepage. And in this case, we'll answer no. And since we have no other existing pages in our application, then the tool asks us to provide a name for the new page that will be created. So we can call it as a new product. Now that it's finished, we can see the result by opening the resulting file here. And so we have the existing home page and we have our new page with the form to create products. Now the second sentence is we say, I want to see a list of products. And again, in this sentence, we are also missing the location in which we want to place a list. So the same as happened before, our tool suggests already existing pages. So now we get the suggestion for the page we created before called add a new product, which will say no. And then we're asked if we want to place the list in the home page. So let's say yes. And in this sentence, we are also missing the details stating which attributes of products we want to see. And so our tool asks for that. It starts by asking how many attributes we want to list. So we'll say 2. And then it asks us to provide the names of the attributes. So we'll say price, name, and price. And now that it's finished, again, we can open the resulting file. And now the home page has a list with the name and the price of all the products we have in the database. Finally, the last sentence is, well, we have this list here, and we want to have a search box to filter the products by name. So we just write that. I want to filter products by name. And in this case, there is no question that the system needs to ask us to conclude. And so now that it's finished, we can reload the application and we see that the home page now includes the search box for us to filter the products. So let's take a look at the final result. We'll publish it. So we have here the list of products in the home page, and we have our page to add a new product. So let's say we want to add an eggplant. Now we can search this list here and see the product that we added.
All right.
This is the starting point of.
Oops. Always plays twice. Okay, so hopefully that gives you an idea. Full disclosure, in the demo, we did mock up the connection between the natural language processing and the back end, is just because the NLP takes a while to respond. We wanted to iterate on the video, but we do have those queries kind of working through the natural language front end. Okay, so I want to say just a little bit about semantics. Actually, there's not a whole lot to say, because the main role of deferred premises is in search for proofs, not in the semantics of those proofs. So if you have an inference rule where A and B are premises and P is the conclusion, and B is a deferred premise, it means the same thing as it would be in an ordinary inference rule. A and B implies P. There's some details here. You have to quantify over the free variables, but that's a standard thing in inference rules. So if you have a derivation of P with a hole in it, then it's really an implication, right? B implies P. If I provide a B, then I'll have a complete derivation of P. So I think there are actually some more things to explore in this logical foundation. This is more Bernardo's expertise on the team than mine, but there's some possible connections between our notion of deferred premises and lax logic, for example, circle A. And so those are things we'd like to explore in some future work. So we did some qualitative evaluation. The context was implementing pages of the Business Insight application, where you can gather information about products and orders and customers in the domain that I've been talking about. What we did was we looked at several sort of commands from users, and we varied the level of detail that the user provided, and also the context. What I mean by context is kind of information available about the existing system. And we just qualitatively looked at what patterns we saw. So in the absence of context, the system basically just asks for the missing details. It's pretty straightforward. You can see it's kind of what we showed, but you can see in the paper some more examples of those kinds of queries and the results. If there's some context provided, like there's existing tables in the database, then we can generate alternatives for the user. What are the pages that something could be displayed on? What kinds of attributes could be shown? One thing we observed, perhaps not surprisingly, is if there's a lot of context, you might get a lot of alternatives. Okay, so I think this means probably, as we scale this up to applications that are of larger size, we're going to need ways of prioritizing those. So AI is one technique. But another thing we've noticed is that simply if the user says a little bit more, it gives a little bit more detail, we can cut those down fairly quickly. So I think this is pretty qualitative information, but I think it's encouraging in the sense that it looks like there's ways of controlling the kinds of blow up that you might see in a search-based synthesis approach. So in conclusion, we want to enable end users to write simple programs. We think that an approach based on logic-based program synthesis could help with this in kind of these domains of simple programs where you're really building systems out of existing kind of templated components that you can plug together. One of the challenges is that end user programmers, who are non-experts, may not realize everything they need to specify. They may leave out details, and so this is one mechanism for kind of dealing with that incomplete information. We can add flexibility to inference rules by indicating that some of the premises are deferred. And so the result is that instead of a complete derivation, we get a derivation with holes that capture the basic structure of the application and allow us to fill in those details later. So thanks to our sponsor, FCT in Portugal and the CMU Portugal program. And I'd also like to thank the collaborators in the larger Golem project, which includes both the natural language team and OutSystems, whose platform we're building on. And I'd be happy to take questions.
So you first. Yeah. Hi. So nice talk. So I was wondering, like, one of the problems with these approaches based on ontologies is the ontology itself. So who provides it? How do you maintain it? How do you envision this?
Yeah, that's a good question. So right now our approach assumes that we're working in a context where there's a lot of libraries to build on provided. So OutSystems provides libraries for building applications, and so we're assuming that this is a setting where they would also provide, the ontology, the inference rules that kind of fits the applications from this domain. Right, so it's not a panacea for all end user programming. I think it's a huge problem to do all the things you might want to do. And of course, Mary alluded to this as a grand challenge in her keynote a couple of days ago. But I think it's for a domain where you have a few more constraints. Right, you're building applications that are kind of in a precedented domain. They could be constructed out of components. You can imagine an ontology that kind of matches the structure of whatever libraries you're putting things together.
Yeah, thank you for the talk, and I like the idea of the logic-based programming synthesis. Just to say, my group published actually Onward paper in 2014 that used the psych knowledge database. And so my question is a little bit related. So it wasn't clear from the talk that you have a basically knowledge base or not, or how big the knowledge base you are using. And for example, if you say product, there was a notion that product is something that has price in like a stock, and maybe there's something is a product that this is. So if the knowledge base has like millions of those facts, that it may be able to do something else. So I'm curious how big the database is.
Yeah, that's a great question. Actually, I don't know if you can invite Joao to the stage. He might have some insights on this if he's available. But I think so. I would distinguish two sources, right? One is a source of knowledge. One is a knowledge base and an ontology that's based on kind of domain concepts and the templates that are available for constructing programs in our approach. The other piece is, which includes things like products. We're not trying to. I think we're not trying to say, oh, there's a universal notion of products that we're assuming some background knowledge on. That's actually something that is constructed by the user for this application. So there's some concepts that are application specific, and those are built as the application is built. And so if you've already built part of the application, then some of those are available as background concepts. But if they're not available, then you would say, one of the things we'd have to ask the user is, what does a product consist of in your world? Yeah, so I think maybe that distinguishes it from the prior work that you did, that maybe is based on an existing large ontology. We're, I guess, less ambitious in some ways to enable this particular kind of component-based synthesis.
Hi, really cool. The question I have is, the user's writing, it's starting with a very natural language description, but then as they get these questions asked of them, the questions seem to get a little bit more structured and programmy, right?
Yeah.
So, I mean, obviously it's still a prototype, but I wonder if there's something about logic-based programs or logic programming that makes it more suitable for asking more natural questions, or was it just that OutSystems was built on a logic programming language and that's why this was the direction the project took?
I don't know that OutSystems uses a logic-based programming currently. They do have this template-based library for constructing low-code applications.
Yeah.
Right now, you can't do that with, to my knowledge, you can't do it with the way we're doing it with natural language. So that's a piece that we're trying to connect, and the role of derivations is connecting these low-level pieces of natural language to the high-level templates that are used, or the application level templates that are used in OutSystems. So we took that off the shelf. I think the role of logic programming is a declarative way of connecting what the user says in these kind of user level facts to the high level things. Now, how flexible that is, I think that's something we have to, explore as we try to support more interesting kinds of applications and domains with this.
Yeah, I mean, I was just thinking like relations, right? They seem to be much more amenable to maybe turning into a sentence, right? Like, is this related to this in this way versus an arbitrary programming language has all of these PL specific concepts in it.
Yeah,
So,
I think the structure provided by the logic is indeed helpful in that respect.
All right. Let's thank Jonathan again.